Check it out now, y'all.
NanoHub U, online instruction.
So in this lecture, we're going to cover the some of the fundamental features that characterize radioactive decay. And in particular, we're going to talk about this alpha, beta, and gamma emission from radioactive nuclei. I'll say up front, my intention is not to turn anyone into a nuclear physicist, but these radioactive decays are discussed routinely in newspapers, and they're commonly discussed within the forum of nuclear safety. So I think it's important for you to at least have some qualitative understanding of what they're about, and also to be able to do some reasonably simple calculations that allow you to predict the energetics of these radioactive decays. So that's the main goal of this lecture, is to just try to provide you with this broad overview of these three radioactive decays that are found among the radioactive nuclides. Up front, I will say that these radioactive decays conserve momentum and energy, and that's simply because there are no external forces that are acting in the process of the radioactive decay. You basically have a nucleus that's unstable, and after a certain period of time, that nucleus decays and it kicks out energetic particles. Because there's no external forces acting in the process of that decay, you can expect that energy and momentum are going to be conserved. So let's start first with the alpha decay example. In each of the three modes of decay, I list a website that you can go to, right? There are simulations on the web that allow you to investigate this alpha decay in more detail than I'm going to run through in this slide. So please, if you have the time and the interest, please check out these various websites. So let's just talk about a typical alpha decay process. So it turns out radium has 88. The nucleus of radium has 88 protons in it. The sum of the neutrons and protons is equal to 226. This radium nucleus is unstable to alpha decay, and that just means that after an alpha particle is emitted from the nucleus, the chemical nature of this particular atom goes from radium to radon, right? And by very careful work, what has been established is that in the process of an alpha decay, a helium nucleus is actually emitted from the nuclear matter, right? And this helium nucleus is given a certain energy, right? It's represented in the early days by the symbol alpha, but we now know it's a helium nucleus. It's got two protons. It's got two protons and two neutrons, right? It's highly charged. It's charged +2. That's one of the reasons why it's stopped so quickly by, let's say, a sheet of paper. The high charge on the alpha particle interacts very strongly with atoms in let's say, a sheet of newspaper, and that interaction rapidly brings the alpha particle to rest. Now, this decay scheme here, right, can be represented by a nuclear equation, and it's important for you to understand how that nuclear equation works. What that nuclear equation says is it says that radium, which has 88 protons, 226 total nucleons, that decays into this element radon, which has 86 protons, 222 neutrons, plus this alpha particle, which we now know to be the helium nucleus, which has got two protons and plus two neutrons. So this is a characteristic way of writing these nuclear reactions, and you can very quickly tell whether the reaction written makes any sense by simply adding up the numbers on the right and left-hand side of the arrow, both for the number of protons and for the total number of nucleons. And if the reaction is a viable reaction, then the sum of the numbers on the right has got to equal the numbers on the left. both for the total number of nucleons involved in the reaction and also for the total number of protons involved in the reaction. So this is a characteristic equation that describes this decay, and it's important for you to understand how to construct these equations, and in particular, how to verify that an equation that's given to you is in fact valid. And the way you do that is, again, just by summing the protons on the right. That's got to equal the protons on the left. And the total number of nucleons on the right has to equal the total number of nucleons on the left. It's a fair question why an element experiences this alpha particle decay, this ejection of this helium nucleus. Fair question why that is. And the answer to that question is addressed in this slide, where we try to calculate the energetics of an alpha decay. So to do that, I just run through a binding energy calculation for the helium nucleus. So this should reinforce the discussion that we had about 2 or 3 lectures back when we first recognized that there was a binding energy associated with the deuteron nucleus, the helium, the nucleus that contained a hydrogen, the hydrogen nucleus that contained the proton and the neutron. Right, so we're going to redo that calculation, but now we're going to do it for this alpha particle. And before I run through the calculation, I want to just try to describe the notation that I use. I use the notation that if I have a small m with a chemical symbol in parentheses, the small m represents the nuclear mass of that object in parentheses. If I use a capital M plus with a chemical symbol in parentheses, that capital M represents the atomic mass of that particular chemical element. So the difference between the nuclear mass and the atomic mass is just the number of electrons that are associated with the particular nucleus, right? And the reason we do this is the nucleus gets heavier and heavier, it's extremely difficult to strip off, let's say, 20 or 30 electrons and just measure the nuclear mass by itself. In fact, all the measurements for masses for the heavier elements involve atomic masses, where, let's say, 1 or 2 electrons have been stripped off the atom to produce a charged object, which can then be measured in some sort of a mass spectrometer. So most of the tables, in fact, almost every table that you see, lists atomic masses, and those atomic masses contain electrons. They contain the chemical elements, right? When we're dealing with nuclear reactions, though, we're dealing with nuclear masses, and so we have to be able to go back and forth between nuclear masses and atomic masses. And the way to do that is to add electrons to the nuclear mass to form an element, and then you can look up the atomic mass of that element in just about any textbook that you care to imagine. So with that understanding, let's think about the binding energy of let's say the helium-4 nucleus, right? So what we've learned from our study from our discussion of the deuteron is that the composite nucleus is more energetically favorable than the sum of the individual parts, and that's going to be a common theme throughout the next 2 or 3 lectures. And that just simply means that if you measure the mass of the helium nucleus, which contains 2 protons and 2 neutrons, that mass is going to be less than the mass of 2 protons plus the mass of 2 neutrons, and it's going to be less by some quantity delta m. And that quantity delta m, when multiplied by c squared, gives the binding energy of that particular nucleus. So the bigger delta m is, the more stable the nucleus becomes, okay? And that's the premise of the binding energy calculation that we're going to discuss. right? So in principle, what we want to know is we want to know what this binding energy is, and we're going to calculate that binding energy from this mass deficit delta M that's required to balance this particular equation. Now, the trouble is, in general, these nuclear masses are not well known, and it's only the atomic masses that contain the chemistry of the atom that are well known. So what we have to do is we have to convert nuclear masses into atomic masses, and the way we do that is by adding 2 electrons to each side of this equation. Because when you add 2 electrons to the left side of this equation, you now have the mass of the helium atom. When you add 2 electrons over here to the right side of the equation, that's just the mass of 2 electrons. So this is a number that we can look up. We know the masses of the proton, the mass of the neutron, and the mass of the mass of the electron. Those are very well-known numbers, and that allows us to calculate the binding energy of this particular nucleus. Now, when we go from the nuclear masses to the atomic masses, we're basically neglecting the electron binding energies. And the reason you can do that is these electron binding energies tend to be on the order of 10 to hundreds of electron volts, where these binding energies for the nuclei, right, are going to tend to be millions of electron volts. So there's orders of magnitude difference between binding energy of electrons to form an atom compared to the binding energy of nucleons to form a nucleus. And that allows us basically to neglect any binding energy shifts that are caused by the electron binding energies involved in this calculation. So, once you've got this equation, then it's a simple matter to solve for the binding energy divided by c squared. You have to look up the mass of the mass of the helium nucleus. That's given in the tables at the end of the textbook. In an exam situation, that number would be given to you. You would just have to know how to use it. Be aware that those numbers are very accurate, right? So you're going to need usually 5 or 6 significant digits in these calculations. You can also look up the mass of the proton, the mass of the neutron, and the mass of the electron. I list those numbers here. Those also have been provided in a previous lecture. And when you work through the numbers, what you find is that the mass deficit delta M is about minus 0.03 unified mass units U. You can convert that into energies by using the conversion between MeVs per c squared and unified mass units U. That's 931.5 divided by 1U. And so what you find at the end of the day that this binding energy for the helium nucleus is about minus 28 million electron volts. And so the question is, what does that number mean, right? It's important for you to have a physical understanding of that number. And what that number means is it simply means that if you produce a helium nucleus, right, these nucleons are bound by 28.3 million electron volts compared to the situation when those nucleons are all far from one another. So again, our zero of energy involves infinite radial separation between these 4 nucleons. When the 4 nucleons are brought close to one another within a femtometer or so, they form this very stable bound state. It's bound by 28.3 million electron volts, and that's referred to as the alpha particle or the helium nucleus. And so now you can answer the question, why do some nuclei decay following the the emission of an alpha particle? Well, the answer is if you have some large nucleus which has Z protons, let's say it has Z protons and it has N neutrons, and if the binding energy of the last few protons plus the binding energy of the last few neutrons, if that binding energy is less than about 28 million electron volts, then it just simply becomes energetically favorable for that nucleus to spit out 2 protons and 2 neutrons to form this very stable helium nucleus, which is in fact bound by 28.3 MeV. So The reason nuclei decay by alpha particle emission is because the highest energy filled states in these nuclear wells have a weak binding energy, and it just becomes energetically more favorable for them to emit an alpha particle, which we just calculated has a binding energy of about 28.3 million electron volts. So that's the simple answer for why many nuclei decay by emitting alpha particles. It's also useful to following the same logic, right, of these nuclear reactions. It's also interesting to ask, what is the energy of the alpha that comes out from from a typical decay of let's say a nucleus? And so to illustrate that point, I'm just going to calculate the Q factor of a nuclear reaction. Q is basically telling you how much energy is released when this particular decay scheme occurs. So in this particular case, I've got the 230 isotope of uranium decaying by an alpha particle emission into thorium-226. And the hypothesis is that some energy is released in that reaction. And since the alpha particle is weighs much less than the thorium nucleus, right, most of this energy we would expect to be associated with that particular alpha particle. So how do you calculate Q, right? Well, it's an energy balance equation. Energy has to be conserved. And so what you have to do is you have to just solve this equation for Q, and Q is going to be the difference between the mass of the uranium nucleus. This is the original parent nucleus, 230 protons plus neutrons. It decays into this alpha particle, so this is the mass of the alpha particle, and this is the mass of the thorium atom. This is the daughter nucleus that's produced in this nuclear decay, right? These are nuclear masses, right? That's what the small m indicates. In order to perform this calculation, you have to convert these nuclear masses into atomic masses. The atomic masses contain all the electrons associated with these atoms, and it's these masses that are measured experimentally. It's very difficult to measure these nuclear masses because in this case, you would have to strip off, for instance, 92 electrons from the uranium nucleus in order to measure the mass of that uranium nucleus itself. That's very hard to do. It's much easier to measure these atomic masses. So, right, what you can now do is you can look up these atomic masses in textbooks. In an exam situation, those numbers would be given to you so that you don't have to memorize these things, but you would clearly have to know what to do with them once you've got them. You do this simple subtraction. Again, you have to keep about 5 or 6 significant figures in this calculation. You can convert the mass difference into energy by using our conversion factor between MEVs and unified mass units. And what you find out that for this particular reaction, Q is about 6 million electron volts. And so then that would allow you to conclude, since this number is a positive value, right, Q is positive, that would indicate that this helium nucleus comes out of this nuclear reaction with an energy of about 6 million electron volts. So it's very energetic, right? And most of that energy is going to be carried away by the alpha particle, simply because the alpha particle is so much lighter than the thorium nucleus. Okay? So that's an example of alpha decay. The next topic would be beta decay, and again, there's a nice website that you can go and investigate and simulate beta decay on the web. So if you have the time to do that, please check it out. The beta decay is basically the conversion of a nucleus which is neutron rich, right? And basically what's happening in this nucleus is that one of the neutrons breaks down, right? It breaks apart and it converts to a proton plus a very energetic electron. And that electron is then ejected from the nucleus and emerges as a beta particle. It was identified as a beta particle very early on, but now we know it's just an electron. And it's very energetic, and it requires sheets of aluminum foil in order to stop a beta particle, right? So it tends to be much more penetrating than an alpha. So a typical beta decay is indicated by this blue box, right? And you should be able to immediately verify whether this is a viable nuclear reaction. So it turns out the lead-82 or lead has 82 protons, 82 electrons in it. The particular isotope lead-214 decays into bismuth, and in the process of decaying into bismuth, it emits this electron. So the electron is -1 protons, and it has no net neutrons or protons associated with it. So the beta particle is represented in this format here. And you can see when you do that, then this summation idea that we discussed earlier on is still works, right? The mass number of the parent and the daughter nuclei, that remains constant, doesn't change. The atomic mass number actually increases by 1. So the 82 protons goes to 83 because a neutron is converted into a proton in this nuclear reaction. Okay, so that's an example of a beta decay process. You can do energetics of that process just like we did for alphas. So for instance, if you want to know roughly how much energy is carried away by the electron, you can calculate the Q factor of this reaction, and you can use that to estimate the maximum energy that this electron that's ejected from the nucleus carries away. The beta decay is interesting because it actually implies something that may not be obvious, right? It turns out that a free neutron, if you could just take a neutron, strip it out of a nucleus and let it move through space, that neutron will actually decay to a proton plus an electron, and it will emit something called an antineutrino, right? So this antineutrino has zero mass. It travels at the speed of light, and we'll say a little bit about why this particular particle is required. But the interesting thing about this nuclear reaction here is that this free neutron lives only for about 10.5 minutes, 10.6 minutes in free space. So even though a neutron bound to the nucleus can exist for millions and millions of years, right? If you take that neutron, you strip it out of the nucleus, it has a half-life, right? It lives for about 10 minutes or so. And then the interesting question is, well, why does this neutron decay into a proton plus an electron plus this antineutrino? And the answer to that question is the fourth known force in nature, which is something called the electroweak force, right? It actually destabilizes this neutron, right? And it leads to this decay into the proton. So we're not going to talk about this electroweak force in the course, right? But it completes our understanding of forces in nature, right? So now there's 4 forces in nature: gravity, electromagnetism, the strong nuclear force that we discussed in the previous few lectures, and now there's this electroweak force that's responsible for this particular nuclear reaction. There's a problem with this reaction that I just want to mention just to be complete, right? Up front, right, you don't measure this anti-neutrino. That's not there. It's very hard to detect, right? And up front, it was realized that there's a problem with spins in this particular nuclear reaction, because a neutron has a spin 1/2, proton has a spin 1/2, and electron has a spin 1/2. So these spins are roughly equivalent to angular momentum. And what you can see is, you can see that angular momentum in this nuclear reaction is not conserved, right? Because you got spin 1/2 on one side, you got 2 spin 1/2s on the other. So these 2 spin 1/2s, you can add the spins up along each other, give a spin of 1, or you can align the spins anti-parallel to one another, get a spin of 0. There's no way that you can produce a net spin of 1/2, which is what the neutron has before it decays. So for that reason, this new particle was invented. It's referred to as the neutrino. And it was Pauli in 1930 who suggested that there has to be some energetic particle with 0 mass, spin quantum number of 1/2, 0 charge. That has to be emitted in this nuclear reaction. And he was able to predict some of the properties of this neutrino. As always in this business, it takes about 25 to 50 years in order to actually verify these predictions, and so this example, there's no exception, right? It required the neutrino was finally detected in 1956, and that discovery was finally recognized with the Nobel Prize in 1995. So just based on very general conservation of energy, conservation of spin arguments, this neutrino was hypothesized, and then 25 years later, it was actually discovered. So if you want to discuss the energetics of beta decay, it's very similar to what we've already done for the alpha decay process. You write down some nuclear reaction. You hypothesize that some energy is going to be released in that nuclear reaction. The question is this value for Q going to be positive or negative? If this value for Q is going to be positive, then that means that there's going to be energy distributed among the products from this decay. So in this particular case, we've got a nucleus actinium decaying into thorium, emitting a beta particle plus this anti-neutrino. We have to convert nuclear masses into atomic masses, right? And we do that by adding 89 electrons to both sides of the equation. We neglect the binding energy of these electrons because we argue that those binding energies are going to be small compared to the millions of electron volts that the nuclei are bound by. Right, so that allows us to replace these quantities in parentheses by the atomic mass numbers of the chemical elements involved. So these atomic masses can be looked up in textbooks. You can do a quick search on Wikipedia to find these numbers. Again, I just emphasize the precision that's required in these calculations. So don't, on an exam situation, don't just keep 3 significant figures because you're probably going to get the wrong answer. And so at the end of the day, what you find is if you work through the arithmetic, you find that about 1.1 million electron volts of energy is released in this particular beta decay. And so that means that the products, the thorium, the beta particle, the electron, and the anti-neutrino are going to carry away something like 1.1 million electron volts worth of energy. So that's how you would do an energetic calculation for beta decay. So I've only got one more left. That's gamma. And the gamma decay is basically you've got a nucleus that's in some excited state. It's got excess energy associated with it. The nucleons in that nucleus redistribute themselves, right? So these energy levels that characterize where what nuclear states these various nucleons exist in, right? those energy levels allow a nucleon to decay from one higher energy state to a lower energy state. And in the process, it emits a photon, which is referred to as, in the early days, it was called a gamma particle, right? And that gamma particle is extremely energetic. It's a photon in the X-ray region of the electromagnetic spectrum. You've got to use lead to stop those photons, right? So the nuclear reaction for gamma decay is written in this form here. The gamma particle is a photon. It has no protons associated with it. It has no neutrons associated with it. So its super and subscript and superscripts are both zero. This star indicates an excited state of the bismuth nucleus, and so this is the way you would represent a generic gamma decay reaction. So I guess the bottom line here is that there are many different types of nuclear reactions that you can write down. It's useful to refer to these nuclear reactions in terms of an entrance channel in which you've got two things that are being combined. These two things combine to form something called a compound nucleus, which is in a very excited state. And then that compound nucleus then decays and it emits a variety of different charged particles in what is often referred to as exit channels. So each exit channel has a well-defined probability of occurring. These numbers have been measured experimentally. And the important point of this slide is that it's just to emphasize this form for a nuclear reaction, right? You should be able, based on this discussion, to figure out what the quantity X is required in order to make a nuclear reaction like this happen, right? And the way you figure out what X is you've got to balance the number of protons and neutrons on both the left and the right-hand side of this equation. So I actually worked through an example. I won't actually spend any time on it. You can check my arithmetic. It's just basically doing the same thing we've done already 2 times in this lecture. But this is the energetics of Rutherford's first nuclear reaction. And the answer to the question, what is X on that previous slide? Well, X has got to be an alpha particle, right, in order to balance the nuclear reaction. And in this case, I calculate the threshold kinetic energy that this alpha particle must have in order for this nuclear reaction to proceed. So I'm a little bit over time, and I got to stop, and so I will. What I will say is the next lecture, we're going to talk about the mathematics of radioactive decay. We're going to try to put some numbers behind this idea that nuclei decay over time. And we'll do some simple calculations that involve predicting how much radioactive material is left after a certain period of time. We'll also review this radioactive carbon dating scheme that you read about very often in the Sunday newspapers. So we'll discuss that as an example of radioactive decay. So thanks for paying attention to this lecture. And come on back and we'll do something that involves mathematics of decay processes.